Yeah, hello everyone. So nice to meet you in this beautiful country. My name is Mengfei Li, and you can call me Phyllis. I'm currently a PhD candidate in the Hong Kong Polytechnic University, the Department of Civil and Environmental Engineering. Today I'm going to share my research on the ductile fracture model of high-strength steel and the shear and tension combined actions. First, I want to give you some introduction. In the structural engineering, the steel with the yield strength over 690 MPa is called the high-strength steel. And in the steel structure, the bolted and the welded joints are the main connections. So the block shear failure on the bolt plate and the puncturing shear failure on the cord is they involves the complex stress state. And this study is aiming to investigate the shear effect on the fracture initiation point under the complex stress state. And to evaluate the stress state, we introduce two parameters. First, the stress traxality is to evaluate the stress concentration, and the second, the load parameter L. This parameter is to describe the deviatoric stress state, and the lower absolute value of load parameter denotes the more intensive shear effect. And here we need to pay attention to two important value. At first, when L equals 0, it means the material point is under the pure shear and plane strain state. And when the L equals -1, the material point is under the uniaxial tension. Then we designed 5 cancel specimens with different notch parts to make sure the fracture initiation part is under the different stress combinations. For example, the standard coupon and notch coupon. Because they are under the axial tension action, so they lies on the bottom line. And when the load parameter is equals to -1, and when the notch part, the radius of notch part changes, the stress traxality increases. And for the shear specimen, the degree of shear stress determined by the central line of the central part and the loading direction. And here is the test setup. We use 3 methods to measure the testing data. First, the extensometer is to record the load deformation curve. And then the high resolution digital camera is to capture the deformed shape during loading. And finally, the DIC system, it can measure the surface strain. Now we see the test results. These 2 figures are the load deformation curve, and the fracture surface of them is observed under SEM. We can clearly see that when the specimen is under the tension actions, the dimples are circular. But when the fracture is triggered by shear, the dimples become small and elongated. Then the numerical model is established in Abacus based on the measured data. And based on this, we can read and compare the stress state of the specimen. And now we can compare the BSC results with the numerical model. And in this figure, we can see the black line is the measured data from the DSC system, and the red dashed line is the simulation results. We can see they are in good agreement, which means the numerical model, this verifies the accuracy of the numerical model. And besides, the deformed shape of the specimen is compared with the picture and the numerical model. And this also verifies the reliability of the numerical model. Then we can trust the stress state from the model. And all the cracks are initiated from the center of specimen and then propagate to the edge. Here I summarized all the stress state of the specimen, the stress traxality, load parameter, and fracture strength. Then plot them in a three-dimensional space. The stress traxality, X, XL, and the load parameter, and fracture strength. We can simply draw a conclusion that with the increase of stress traxality, the fracture strength sharply decreased. That's just our common sense that with more intensive stress concentration, the specimen is more likely to fracture. But how about the influence of load parameter? And what happens when load parameter changes? Here, I draw the test data from of the axial tension conditions L equals -1, and the pure shear and plane stress condition L equals 0. You can see the yellow line is much lower than the blue line. That means the existing of shear stress will lower the fracture strength. That is, the shear effect would bring forward the crack initiation. And now we see this space in the side view. And when the stress traxality is equal, the effect of the load parameter on fracture strength is nonlinear. It decreases first, then increases. And based on the findings, the new ductile fracture model for high-strength steel is proposed. We already know that the axial tension state and the plane stress state are the two boundaries of the fracture surface. And they can be expressed with the exponential functions, the classical rising Tracy model. And then the effect of load parameter is in a quadratic way. So the expression of the fracture model can be expressed by this. A, B, and C are the combination of the two boundaries. When the L equals 0, the fracture surface degrades to the plane strength state. So based on the known 2 points in here, we can calibrate the fracture model. And the final expression is like this. Then we use the data point to calibrate the fracture surface, the three parameters C1 to C4. And the calibrated model, the fracture surface is plotted in this figure. And when we use the calibrated model to predict the fracture initiation of the specimen, we can have the prediction error is around 10%. And the curve is well with the testing data. So the future work will focus on the application of the proposed model and the comparison with other classical fracture models. So if you are interested in our work, you may scan the QR code and check our newest research. Thank you very much.